last class we looked at Dijkstra's algorithm for computing the single source shortest paths. The algorithm, I do not recall if I did tell you the name of the algorithm, it is called Dijkstra's algorithm. Yeah. And what remains to be done, we have seen what the algorithm is, hopefully you all understood. I am going to be revising it in any case today. We had also argued how to implement the algorithm, yeah, and what its running time would be. Right. The implementation was very similar to Prim's algorithm for computing minimum spanning trees with some small modifications, and but we have not argued of why the algorithm is correct, why Dijkstra's algorithm is correct. Okay. So, as a quick recap of what is being done in Dijkstra's algorithm. So, we are given a source vertex, we are given a graph, there are, you are given a length function on the edges are non-negative, right. You can have 0 edge lengths, but you cannot have a negative edge length, that is important and we will see why. And what is happening at each point, right. At each point we have, so with each vertex we have a distance label associated with that vertex, d of v, right. And we will today what we have to do first is to understand the semantics of this, what do these numbers represent. Yeah. Initially d of v, recall, is infinite for every vertex. D of v is an upper bound on the distance of v from S, upper bound, okay. And this quantity with every step only decreases, it never increases. At a particular step, what does the algorithm do? So, at any point we have two sets, capital S and S complement. The vertices which are in S, for them we have computed their actual shortest path distances from S, we have already computed that. And the vertices which are in S complement, for them we do not yet know the correct distances, we only have an upper bound on the correct distance. Yeah. So, at a particular iteration, what do? We take the vertex for which the dv is minimum. Yes. Suppose this is the vertex u, right. So, du is less than or equal to dv for all v in S complement. ठीक है, just signifying the fact that इसका जो है सबसे कम है distance label, and then we are going to move u across. U will go from S complement to S. The claim is, we will also have to make this claim to argue correctness, that at this point जो भी du की value है, that is the correct shortest path distance of u from S. Yeah. Okay. When we move u across, how do we update the other labels? If there are, my favorite is 3, if there are 3 edges going out, yeah, of u to other vertices in S complement, ये एक vertex w है, तो what is the new distance label of w? Min of dw d of u plus length of the edge u w. This is how we update the distance labels. ठीक है? As you can see, this operation shows that dw की value will only decrease, it cannot increase, because it is the minimum of two quantities, one of which is d of w. Yeah. So, d of w की value will only decrease. So, if these distance labels were sitting in a heap, then all you will have to do is to do a decrease priority operation on the heap. And when you are removing the minimum, that corresponds to a delete min operation from the heap, right. This is just a recap of what we have done in the last class, you have seen all of this before. Okay. So, that is the algorithm, we keep doing this till everything moves from here to here and then we are done. What is the initial composition of S and S complement? Initially the only vertex in capital S is little s, yeah, and everything else is in S complement. Any questions to this point? Okay. Now, let us first understand what d of u means. Given a vertex u, what does d of u mean? Right. So, given a vertex in S complement, a vertex u in S complement, this is S, little s is here. What is the meaning of d of u? What connotation, what semantic can I associate with d of u? Shortest distance of a path, shortest length of a path, okay. Including vertices only from?
Only the last vertex will cross.
Yes. Right. So, claim is d of u is the shortest path from S. So, let us look at all paths from S to u which only use vertices of S, and at one point they take one edge across and reach u. Right. इस तरह के बहुत सारे paths हो सकते हैं. There can be many such paths. This is one path, maybe there is a second path which goes like this, right. There is maybe a third path which goes like that, and so on and on, right. So, there could be again a whole lot of such paths. Let us compute the length of all of those paths, and let us take the smallest amongst those, that is d of u. So, formally I could write d of u equals length of shortest path from S to u that includes only vertices from the set S. Right. आप कहेंगे u तो S complement में है, तो except for u which is the last vertex, the other intermediate vertices will only be vertices from S. That is the meaning of d of u, or that I claim is the meaning of d of u. Let us see whether this is really true. Yeah. How will we prove that this is true?
Because if there exists a path from S using the vertices of F bar to U, when we have added that vertex, we would have taken whatever the value is U at that point, we have taken the mean. So, we would have reached the mean.
Okay. So, the best way to do this is to prove it by induction. Yeah, makes sense to try and prove it by induction. So, we will assume that at this point this is true. The numbers or the d on these vertices do actually reflect this quantity. Yeah, and then we will say when I move one vertex across, then the new d's on the vertices continue to reflect the same thing, right. And then we will show what that the base case is also true, and that will establish this claim. Okay. Now, if it is true now and I move a certain vertex across, let us say vertex w which is here moves across. Okay. As a consequence, I might end up updating the distance label of u, right. I will update the distance label of, so this edge is not there, sorry, this edge need not be there, this is just signifying that this vertex moves across. Let us say u, u1, u2, u3 are the 3 neighbors of w, out neighbors, right. So, we are going to update u1 to d of u1 equals minimum of d of u1 comma d of w plus L u or w comma u1. Yes, this is how we are going to update. Okay. Why is this correct? Why is it that after this the new value of d of u1, maybe it is the new value, maybe it is the old value, still satisfies this thing? Yeah. So, if d of u1 remains unchanged, then that means that this the earlier value was the smaller one. Okay. So, what is it that is happening? So, w moved across. Let me draw this picture now. S complement minus w plus w. Okay, w is here. u1 is here.
So now we have got another path for u1.
Not another path, but I should say now let me look at all the paths from S to u1, right. Okay. Now, those paths, what could they be doing? So, I have to look at all paths from S to u1 which only include vertices from this side.
Initially we were having all, initially the paths were having.
So, either the paths do not include vertex w at all and they go directly like this, right. Either they do not they do not include vertex w and go directly like this, but then the length of such a path is already captured in the earlier value of d of u1, right. D of u1 is smaller than the length of all such paths, or such a path includes w, right, and then. So, one possibility is that it includes w, that it visits w and then goes to u1. A third possibility, yeah, it goes to w, goes to some other vertex and then goes to u1.
So third case is not possible. So the third case is not possible. So because
Okay, let us look at these three things. You understand that these are, so we are saying either it does not visit w at all, which is this first case, right. Then either, okay, so then what remains is it visits w, right, it touches w. What touches w? We are looking at the shortest path from S to u1, which includes only these vertices, right. So, the other case is that it touches w and then the moment it hits w, after that it goes directly into u1. This is the second case. Third is it comes to w, then it goes off somewhere else and then it goes to u1. Okay. Now, what?
so third
Now, you are claiming the third case cannot happen. What do we mean by cannot happen?
all the outdated vertices of w line as well.
You don't have to consider third case because that is always going to give you a length more than
So all the outdated vertices.
So, such a path, claim is that this path has length at least as large as d of u1.
D of W1, D of W1 plus
So we use that property that in the shortest path, the path to every other vertex is shortest. So if this is the shortest path, then path to S to W must be shortest, and then from W to U must be shortest. And
No. What is it? Why? Okay, it is right that we have to look at these three cases one after the other. So, case 1 is covered, right. Case 2 is also covered. Why? Because this path comes up to here and then I take this edge. So, this the path from S to W
is the shortest path from S to W.
is the shortest. So, this, if this is the shortest path from S to u1 and it goes via W like this, then this part has to be the shortest path from S to W. That is equal to of length dw by your induction hypothesis, right. And then this plus this length would be the length of this path from S to u1. So, that is getting captured here. Yeah, we are accounting for the length of such a path. Now, what remains is this case 3. Why can't we have this?
Because length from S to U will every.
Let us say this vertex is x. Now,
The S to W has to be the shortest path by the shortest path property.
okay,
Then if S to W is the shortest path,
right.
then this path, the other path S to W, the length is either greater than
if
or
X
equal
is
to.
there, then if X
No, you are wrongly concentrating on W. It has to be x. You have to look at x.
So SWX cannot be the shortest path because W is added in this step only.
On this step only, x was added
Before this,
before
there was
this.
another shortest path from X to X.
Right. So x was already there. So we already knew shortest path from S to X. Right. We already knew the shortest path from S to X.
Which we have dealt with in case 1.
Right. And that was equal to d of x, the label on x.
And it didn't involve W.
And it doesn't involve w or whatever. We already have that information, right? So this, if this is the shortest path from S to U1, yeah, then S to X, this is also the shortest path from S to U1. What is this blue line that I have drawn? This is the shortest path from S to X. You can't see the blue line. This is this one. Yeah? You understand why missing? Yeah, X was already a path of S, which means we already had the shortest path from S to X. And the shortest path from S to X is using only vertices of capital S, not using W at all. And that path sits here. So the shortest, if this longer path, if this path which goes from S to W, then from W to X, and then from X to U1 is the shortest path from S to U1 using vertices only of S plus W, then this path from S to X followed by X to U1 is also the shortest path. Yes? And if it is also the shortest path, then we have already accounted for it in d of U1. D of U1 is only less than this quantity. Because what is d of U1? D of U1 till now is the length of the shortest path from S to U1 using vertices only of capital S. So this path that I have now created doesn't use the vertex W at all.
So this is like case 1 only.
So it becomes something like case 1, except that you have to make this argument.
Sir, this will would be greater than d of U1.
Okay, so maybe all of this is not very clear. Let's try and do it more completely. So we are looking at S, we are looking at U1, right? And we are looking at W is the vertex which has just come in. Yeah? And we are looking at this third case when the shortest path from S to U1 goes via W to a vertex X and then it jumps across to U1, right. Now the length of this path, which is S to W plus W to X plus X to U1, the claim is that the length of this path is at least as large as the length of this path from S to X followed by X to U1. So let me write that down. Length of path S to W to X to U1 is no less than that of the path S to X to U1, where what is the path from S to X I am taking? The shortest path from S to X. That does not include W. Shortest path from S to X does not include W. Why? Because W just came in, yeah, and X was already there, and by our induction hypothesis we had already found out the shortest path from S to X, and that is a path which is lying completely in S. Yeah. So let me write that part down also. Shortest path from S to X does not include W and includes and only includes vertices of capital S. This is capital S plus W now. This is capital S complement minus W. Capital S was the part before we moved this thing. Okay? Everyone follows this? Right? So, this path which is going like this has length at least as large as the length of this, right. But what do I know about this? About this I know that d of u1 is less than or equal to this length of path s to x to u1. I already know that, yeah, because this was the smallest, d of u1 was the smallest possible path which did not use any, which used only vertices of s, yeah. So, this is only less than that, and since this is less than this, d of u1 is less than or equal to this longer path, and so I can effectively ignore this thing. I do not have to consider it because it is already included in my d of u1. d of u1 is already a smaller quantity than that. So, all such paths are captured in d of u1. d of u1 is a quantity only smaller than such paths. The one path which is not captured is such a path which goes to w and then takes an edge out, case 2, and for that we have included it here. Right. And the smaller of these two will give me now the smallest path from S to u1, which only includes vertices of S plus w. Okay. Questions? कुछ नहीं समझ में आ रहा है? कुछ नहीं समझ में आ रहा है या कुछ नहीं समझ में आ रहा है? बताइए. Great. So, that is the semantics, and once you have that semantic in mind, then it is easy to prove most of the other things, right. What is the meaning of those distance labels? Once you have that in mind, then everything else follows very simply, right. So, everyone convinced that d, the distance label, reflects this kind of length, right. So, now why are we justified in moving the smallest label vertex from here? That is what we are doing at each step. Yes, at each step I am taking this vertex which has the smallest label and moving it across and claiming that it has the right number on it. Why am I justified in doing this?
Any path which includes only vertices from S, this is the smallest path. For any path which does not, which includes vertices of S bar also,
Right.
their d of u is greater. So any path which includes those vertices, the length will always be greater.
Because we will be including an edge UW also, at least one edge UW if we take path from S to W via U, which is in S bar.
Good. So, the claim is, so now what we are claiming is d of w is the length of the shortest path. What is w? W is the vertex which has the smallest label. W is the vertex with the smallest d value in S complement. The claim is that dw is the length of the shortest path from S to W. Why is this claim true? Well, proof by contradiction. Suppose this is not true. Okay. Now, if this is not true, what does that mean? That there is a shorter path from S to W. Yes. Shorter than what? Shorter than dw. What will that path do? That path will visit some vertices here, and at some point it has to jump across. Yeah, and then it has to come to W. Right? Maybe it jumps back and then comes again. Right? It could do a whole lot of crazy things, but it has to at least jump across once. If it jumps across once, let us say it jumps across and reaches vertex x, then what is the length of this portion of the path? greater than or equal to d of x. That is our semantic that we have associated with d of x. So, this part of the path is at least d of x. This part of the path, यहाँ से यहाँ तक का. Why? Because we said the shortest path from S to x, which uses only vertices of S, has length d of x. Now, this is a path which uses vertices only of S. So, it has length at least d of x or more, which is why I have put the greater than or equal to. So, this part of the path is length at least d of x. So, which means the entire path has length at least d of x. Here I am using the fact that edge lengths are non-negative, right. So, this entire path that we have drawn has length at least d of x. Yeah. So, this path, so path drawn has length greater than or equal to d of x, which is greater than d of w. Or greater than or equal to, maybe they were the same distance labels, right. So, this path has length at least as large as d of w, right. So, which means it is not a shorter path. We started off by saying that, well, there is a shorter path than d of w, there is a path whose length is strictly less than d of w. So, that is not the case. If there were such a path, it will have to have a length greater than or equal to d of w. It cannot be strictly less than d of w.
So, this path which we have considered from the S to x is the, if we have taken the shortest path, that we have taken to any path.
No, you said this is the best path, right. So, all I am saying is this part of the path has to have length at least d of x. If it were the shortest path, then it would have exactly d of x, but maybe you did something, I do not know, it is at least d of x. Okay. So, d of w tak there is no path which is, sorry, w tak there is no path which is smaller than length d of w, there is no path at all possible. Yes or no? There is no path from S to W of length strictly less than d of w, which means d of w is the length of the shortest path from S to W. And so, we are justified in moving this vertex across, because we have found the length of the shortest path from S to W, right. And what is that path? That path would include some vertices from here and then jump across. Yeah. So, we are justified in moving this vertex across. Now, this entire thing, so okay, now let us recap the argument. We said we would do an induction on what are we trying to prove? Sorry, let us back up. Huh? No, this we have done, this claim is okay, right, but isse pehle we were proving this. Length of shortest path from S to U that includes only vertices from S equals d of u. This we were proving using induction, and in this induction, one part of this induction, in proving this induction statement, we required that क्योंकि x already यहाँ exist करता है, so we have found the shortest path from S to x already. Yes. And that we have proved now. नहीं आया समझ में? How will you? Huh? We apply. Yeah, induction is being applied on the number of elements of S. So what is the induction statement now? So what? Who will tell me what should be the induction statement? Right, I have told you everything. Now you need to just churn it in your head and figure out what is the right induction statement to make. this is S and this is S complement.
D of x is the smallest path from the source to x containing the elements of S, and if x is in S bar S, then it is the smallest path required.
D of x is the smallest path for all the paths including the vertices from S, and x is all the vertices in S and the element which you are moving.
Okay.
from that.
So, the induction statement should be for all x in S. What should I write after this? D of x is the length of the shortest path from S to x. For all x in S complement, d of x is the length of the shortest path from S to x, which includes only vertices of capital S. ठीक है, ये दोनों statements will have to be part of your induction hypothesis. Now, how will this work? We will do the base case later, right. So, now we say there is this vertex W which we move from here to here, right. Since it has moved from here to here, we have to argue for vertex W that d of W is the length of the shortest path from S to W, right. That we did here, d of W is the length of the shortest path from S to W. For the other vertices in S complement, we have to argue this statement, right. For the other vertices in S complement, we have to argue this statement that इसको मूव करते समय हमने बाकी वर्टिसेस के लेबल्स अपडेट करे, राइट. तो वो जो अपडेशन है वो इस तरह से है कि दिस स्टेटमेंट इज स्टिल ट्रू एंड दैट वी हैव डन ऑन दिस स्लाइड. d of u is the length of the shortest path from S to u, that includes only vertices from S, right. So, we basically, this was vertex u1, we looked at these three cases, ये हमने vertex यहाँ मूव किया. अब जो shortest path है from S to u1 which only includes these vertices from S, right, that either includes the vertex W or it does not. If it does not include the vertex W, then we know that the length of such a path cannot be no more than d of u1. If it includes the vertex W, then its length, if it were such a path, its length is no more than d of u1, but if it were such a path, case 2, then its length is exactly this, right. And so, the minimum of these two quantities is the length of the shortest path from S to u1, which only includes vertices of S plus W. ठीक है, उससे हमारा ये वाला स्टेटमेंट भी प्रूव हो जाएगा इंडक्शन स्टेप का फॉर द अदर वर्टिसेस. बेसिकली सब वर्टिसेस के लिए ये स्टेटमेंट प्रूव करना है हमें, राइट. तो यहाँ वाली जो वर्टिसेस हैं उनके लिए तो ये स्टेटमेंट कंटिन्यू, इट विल कंटिन्यू टू रिमेन ट्रू बिकॉज वी हैव नॉट चेंज द डिस्टेंस लेबल्स एट ऑल. What have we changed as a result of this? We have moved one vertex from here to here and changed the distance labels of these vertices. Since we change the distance labels of these vertices, we need to argue this statement for those vertices, and since we moved this vertex from here to here, we need to argue this statement for this vertex, and we have done that. हाँ, क्या रह गया?
Can we combine the two statements into one statement and by saying that for all x element of set of vertices, we have to prove dx is the length of shortest path from S to S vertices from S.
Which only includes vertices of S.
We skip the first statement.
And we write x element of all the set of vertices.
You take any path, any vertex that belongs to x, you read this.
No, you don't want to say, देखो उसमें प्रॉब्लम ये होगी, if you just say that for all x, d of x is the length of the shortest path which includes only vertices of S, right. So, when W comes in here, you will have to now look at all the vertices in there and also argue that by W coming in, the length of their shortest path is not reduced. Because W only comes in now. ठीक है, तो वो थोड़ा सा ज़्यादा कॉम्प्लिकेटेड हो जाएगा प्रूव करने के लिए. दिस इज एग्जैक्टली व्हाट द थिंग इज. जो वर्टिसेस S में है उनके ऊपर नंबर आर द राइट नंबर्स एंड दे विल नॉट चेंज. दैट्स द लेंथ ऑफ द शॉर्टेस्ट पाथ फ्रॉम S टू दोज वर्टिसेस पीरियड. एंड जो वर्टिसेस S कॉम्प्लीमेंट है उनका जो नंबर है दैट इज क्वालिफाइड इन अ सर्टेन वे. दे आर द लेंथ, दैट्स द लेंथ ऑफ द शॉर्टेस्ट पाथ फ्रॉम S टू दैट वर्टेक्स, provided the path uses only vertices of capital S. ठीक है, that's the qualification to the path. बस आप ये ध्यान रखेंगे सब प्रूव हो जाएगा. This is the property that you have to keep in mind about these things.
And for vertices of S, what we need to we simply say कि because it is the shortest path, we use the vertex so it is true. We want to say कि for initial condition we are showing when we are saying कि for vertices of S we have to say that is the length shortest path from S to X. For proving that we how do we do that?
No, for the vertices which are already here, it is the same, right? We have not changed the distance label for those vertices at all. If earlier it was true that for a vertex which was here, the D was the length of the shortest path from S to that vertex, then it remains, right? It's the shortest path, unqualified. This is not qualified saying ki ye this is vertices of S or any such thing. It is the shortest path from S to that vertex. Yeah. So now let's do the base case. Right? What is the base case? But base case is very simple. Right? Your S has only little s in it, and S complement is everything but little s in it. Okay? And इसके ऊपर क्या है हमारा शुरू में डिस्टेंस लेवल 0 है, राइट? एंड इन एजेस पे हम क्या डिस्टेंस लेवल्स डालते हैं? Basically length of this edge only, right? We start off by putting these as infinite, but then the moment we move this across, right, this will get the length equal to this. So if this was 7, this was 12 and this was 3, then these would get distance labels 3, 12 and 7. And is this correct? Is this the length of the shortest path from S to this vertex which uses vertices of capital S only? Yes. So there is no other vertex in capital S. So there is only this one edge, and so it is the length of the shortest path, right? And similarly for this and similarly for this. So it's correct. The base case is correct, and at each step we are maintaining these two properties. This is what you have to keep in mind.
Sir, for the base case we have to take any example.
Take any?
Take any example for that.
What do you mean example?
Example.
Huh?
Example mean example, like you have taken.
Huh? ये 7, 12 or 13? You just have to say if this is length L1, this is length L2, and this is length L3, then this will have L3 on it, this will have L2 written on it, and this is length L1 on it. Right? And these need not be 3 edges, there can be any number of edges. Yeah? There is no example here, this is a proof for any graph. ठीक है? ये समझ में आ गया सबके? So इस तरह से, so that argues the correctness of this algorithm. So this algorithm is due to Dijkstra. J is pronounced Y, so it will become D-I-Y-K-S, Dijkstra. Right? Okay, and what did we argue is the running time of this algorithm? Yeah? Okay. What is okay? This algorithm would not work if the graph had edges of negative lengths. Okay. In fact, if a graph has edges of negative length, right, then there is there is no notion of a shortest path sometimes. Huh? Do you understand what I am trying to say? Suppose this were my graph. Pardon? Recursively, repeatedly, right? So, for instance, there is the shortest path from length from S to T has length minus infinity. Yes? Why? Because I will start from here, I will go down, I will come back and keep going. With every turn I make of this, every time I go around the cycle, I get minus 1. So, I will just keep doing this. Yeah? So, the problem is because you have a negative cycle. This is called a negative cycle. So, if the graph has a negative cycle, then shortest path not defined, or there is no notion of a shortest path anymore, because the length of the shortest path could be minus infinite, right. But this graph need not have a negative cycle. For instance, if this edge had a length of minus 1, right. Now, what is the shortest path from S to T? Length 1. I would go like this, come down and then go like this. What would be the length of this path? 1. When do you think negative lengths make sense? So, is this very artificial negative lengths? Can you think of a setting where
somebody pays you to go from one place to another?
Somebody pays you to go from one place to another. When would that happen?
When somebody isn't there.
You gain some petrol.
Yes, sir, we don't have to pay. Somebody pay for our petrol.
Okay. What other settings can you think where you can have a negative resistance? So, one other setting that I saw somewhere was suppose these are this is a graph which represents currency tradings. Okay. Now, it is a different, you can think of it in a different setting also, right. So, each node is a currency, you are a hotshot whatever global currency trader, if there is such a, right. And then an edge reflects that if I change from, if this is let us say rupees and this is what Indonesian baht, then then this is the profit I incur in doing that, right. And negative would then correspond to a loss because of whatever exchange rates at that point in time. Yeah, and then you want to finally change your rupees into, let us say, back into rupees, right. So, what you are seeing is if there is a positive cycle in this graph. So, then you will just keep going around that cycle and keep making money. See? हाँ, तो वहाँ shortest path नहीं, आपको वहाँ longest path चाहिए, हाँ? Frequent flyer programs, right? Right. Okay. So, I do not understand your example, but there are many such settings you can think of where negatives would make sense also. Okay. Now, How can I solve this? How can I find out the shortest path in a graph which has negative edge length? Or first, can Dijkstra's algorithm work? Does Dijkstra algorithm work here? Huh? Keep the minimum as 0. And so shift, increase everything by +1 by the minimum, right? तो यहाँ पे इस एग्जाम्पल में सबको जो है हम +1 कर दें, प्लस so that you don't have a negative, right? So add a sufficiently large number so that there is no negative length, right? So brilliant idea, except that it doesn't work. ठीक है, आप कह रहे हैं कि you add a delta x so that everything becomes positive. Why does this not work? Number of edges, yes. Number of edges on one path could be different from number of edges on another path. Yes. So suppose I have a very simple graph. ठीक है, अब what am I trying to show you? Okay, so what will I do? Okay, so I want to, what do I want to, let me just finish this example first. So this path is the shorter path, but its length increases because there are a lot of edges on it, right? So let's say all edges had length 1 on it, and one edge had a length of -1. So what is the length of this path? The length of this path is 3, 4, 7, -1, 6. Yeah, and let's make this path of length longer than 6. So let's make it 3, 3, 3. This becomes 9. Now if I increase everything, or let me make it 3, 2, 2, just to be on the safe side. So it's 7. So it's longer than this. So this is the shortest path. But if I now increase every edge by 1, then what is the length of this path? +1, +1, +1, +1. 7 edges हैं, 1, 2, 3, 4, 5, 6, 7, 8 हैं, तो ये +8 हो जाएगा, और ये कितना हो जाएगा? +1, +1, +1. इसकी लेंथ हो जाएगी 3, 6, 10. तो आप ये वाला ढूंढ लेंगे, ठीक है, पर ये तो शॉर्टेस्ट था नहीं ओरिजिनली. हो गई गड़बड़? What do you mean reconvert back? Keep track of number of edges. How will you keep track of number of edges on the path? आप shortest निकाल रहे हैं, तो आप number of edges भी कैसे keep track करेंगे?
So, but if the edges are negative, there is no notion of a shortest path.
No, there is a notion. There is no notion of a shortest path if there is a negative cycle. But the graph need not have a negative cycle, as is, let's say, this graph. There is no negative cycle in the graph, right? नेगेटिव साइकिल होगी तो क्या होगा? आपका फिर -∞ हो गया, ठीक है, क्योंकि आप उस साइकिल तक जाएंगे, उसके घूमते रहेंगे, और फिर जब बहुत थक जाएंगे तो आप बाहर निकल जाएंगे, ठीक है. तो -∞ हो जाएगा. जितनी देर आप घूमते हैं उतना कम आपका लेंथ हो जाएगा पाथ का. पर अगर नेगेटिव साइकिल नहीं है तो इट्स वेल डिफाइंड. सो फर्स्ट टेल मी व्हाट goes wrong in Dijkstra's algorithm. Where does it break down?
So we use that path from say S to X.
This will be minimum.
D of X greater than D of W. Then from X to W.
Every shortest path from
The path is again greater than D of W. We assume that path then.
Right. So did this argument break down? So here we argued that D of U is the length of the shortest path from S to U that includes only vertices from S. Does this break down?
Yes, sir.
The other wala breaks down. This doesn't. This is okay. This part of the argument is fine, I think.
It is only when we have added W to
Right. But this part of the argument when we said that dw is the length of the shortest path from S to W is not correct anymore, right? Because I could have a path which goes like this, right? But this is shorter than d of W because there are plenty of negative edges on this part. So that this inequality is not true, right? Because यहाँ तक का पाथ की लेंथ तो d of x थी या d of x से ज़रा ज़्यादा थी, पर उसके बाद ये इतना नेगेटिव हो गया कि वो d of w से कम हो गया. So now I cannot say anymore that d of w is the length of the shortest path from S to W. So this thing breaks down. So Dijkstra's algorithm does not work. You cannot use Dijkstra's algorithm to compute shortest path if you have negative edge lengths. So वो नहीं काम करता. ये आपका ट्रिक कि सब में जो है हम प्लस कर दें, वो भी काम नहीं करता. तो how are you going to make your millions?
When we only updated the values of the vertices which are in S bar. If we update the vertices which are in S also, we wouldn't do it.
How will you do that? You have to tell me what.
So because whenever there is an out edge to it, at the length, just like we update the vertices of the S bar, we update the vertices of S. So if there exists a path from which after coming of W, there is exists a path from W to that, and that is a shorter path.
So if we can put a lower bound on the shortest path, we can calculate it in some way that it cannot be lower than this one.
Okay, so this is a valid question here, right? We'll basically not discuss it today because we don't have the time to do it. So that's one thing that remains to be done कि अगर negative edge lengths हैं तो आप क्या कर सकते हैं, कुछ कर भी सकते हैं या नहीं कर सकते, पहली बात तो ये. और दूसरी बात रहती है कि हमने अभी तक बस शॉर्टेस्ट पाथ लेंथ कैलकुलेट करी है, शॉर्टेस्ट पाथ नहीं कैलकुलेट किया. हाँ, तो ब्रीफली वो भी कर सकते हैं. और कैसे कर सकते हैं? Everybody has a linked list of edges. What does it do with the linked list of edges? What is a pointer? Where does it maintain a pointer to?
So for every vertex we remember the previous one.
Previous one, yes. जैसे हम यहाँ du1 equals min of du1 comma dw plus lw comma u1 करते हैं. अगर ये min इसकी वजह से आता है तो इसका मतलब u1 को जो शॉर्टेस्ट पाथ था वो w से होके जा रहा था. ठीक है, और वो क्या पाथ होगा? वो होगा शॉर्टेस्ट पाथ फ्रॉम S टू W एंड देन द एज W u1. ठीक है, तो हम u1 पे बस ये रखेंगे इंफॉर्मेशन कि u1 तक का जो शॉर्टेस्ट पाथ था वो W से होके आ रहा था, और W पे हम क्या इंफॉर्मेशन रखेंगे कि वहां तक का शॉर्टेस्ट पाथ कहां से होके आ रहा था, एंड सो ऑन एंड ऑन. तो इस तरह से हम बैक ट्रैक करते हुए जब रूट तक पहुंच जाएंगे, सोर्स तक पहुंच जाएंगे, तो हमें पता चल जाएगा कि पाथ क्या था. So we are going to look at it in more detail in the next class, right? How exactly you are going to do it, right? What is the modification to the code that will be required to do such a thing? So that's one thing I would like to cover, and the other thing I would like to cover is also to show you an algorithm to compute shortest paths when you have negative edge lengths. Okay? But it's going to be very different from this algorithm. Okay, so these are the two things that remain. We'll take this up in the next class. Okay.